Announcements. I did grade activities 5 and 6. I emailed Saturday 2 or 3 attachments. One was calorimetry. We're now in chapter 10, but I am going to review dilution at the beginning here in a minute. The only part of chapter 10 that we emphasize will be endo and exothermic, which I think y'all have been taught, and calorimetry and Hess's law. So today is going to be dilution review, since your lab this week's Beer's law. And then I'm going to start calorimetry. I just emailed a homework practice that you should try for Wednesday. That way, if you've got questions, you can email me or I'll answer them on Wednesday. But basically, the little practice that I emailed deals with dilution, several ways we can ask it, and then a couple, 2 or 3 calorimetry problems, which I'm going to go over that main formula here in a little bit. So I'm going to start. I sent a sheet on molarity over a week ago, and at the very end of that molarity handout, it had the formula for dilution. Y'all let me know if I need to pull it up, forward, back. Do y'all see the dilution formula? It basically is saying if you know an initial volume and an initial concentration called molarity, and you're given one of these 2 values as the end or final result, you can solve for the fourth or the other one. Volume, if it's in liters, molarity is moles per liter. That cancels. So basically what this dilution formula is saying, initial moles will equal final moles. So it's just a formula with 4 variables. You have to be given 3 of the 4 to solve for the missing 1. So can I go to the next sheet? This was just a quick review on dilution, because your lab this week, you have to use this formula 5 or 6, 7 times. Okay, I've done, again, this is quick because it's a review. I've done, let's see how many, 3 quick examples. This one says, what volume of 18 molar acid is needed to prepare 400 milliliters of a much more dilute concentration, 0.300 molar. Of, in a word problem, means to multiply. So that's actually telling you the numbers that go together. So what I've done is I use my dilution formula. I don't know the initial volume. I know the initial concentration, which is very concentrated, equal, I know my new or final volume and my new or final concentration, which is a dilute concentration compared to the 18 molar. Maintaining significant figures, I solve and I get the 6.67 milliliters. We good? Let me know if I'm going too fast. I'm just trying to review this. The next 2 are very important with how we word it. One of them, this one is going to say is added to a volume of water. The other one's going to say is added to enough water for the total volume. So this is version number 1. Determine the new concentration when 10 milliliters of a concentration solution is added to 10 milliliters of water. When it says added to, you actually add those 2 volumes together. So 10 milliliters was the initial volume. This is the initial concentration. You are diluting it with 10 milliliters of water. So now your total volume has been increased to 20. So you just solve for your new concentration. We good with this? Now, notice it says added to a volume of water. Look at this one. This one is saying added to enough water to make. And now I'm giving you the final volume is 50. So this one is determine the new concentration when 10 milliliters of 0.325 molar is added to enough water to make the final volume. So you don't add the 10 and the 50. You do not do that. The 50 is your last or final volume. So again, you plug in and you solve for your new concentration. So I just wanted to point out those two ways we can word the problem. One of them, you have to add the two volumes together, and one of them you don't. Okay, so that was my quick review on dilution. Are we good? Anybody need, oh, let me add this person in. Where's my roll? Are we good with that? Okay, now new topic. And this is now chapter 10. We're only doing, I think, the first 5 or 6 sections of chapter 10. Again, I've sent the lecture notes already for calorimetry. The main formula, well, let me say this. If heat or energy is required or needed, that means endothermic, and the value for the delta H or the energy would be a positive value. If energy is released or produced, that's exothermic, and the value for the delta H or the energy would have a negative sign to show that it was released. The main calorimetry formula, and these are in my lecture notes, I'm just writing it out, Q, which stands for heat, MS delta T, which means heat equal mass, mass is in grams, specific heat is your S, and that has a unit. It's joules per gram degree Celsius. It's a combo unit, so it will never, ever limit your significant figures. And then the change in temperature, the temperature will be Celsius. So this is your main calorimetry formula. And on test, as we usually provide this formula. Now, I haven't decided how I'm going to do this last test, so, but I will allow this formula. Okay. Specific heat can also be in terms, instead of joules per gram degree Celsius, it can be in calories per gram degree Celsius. There's a conversion, 1 calorie is always 4.184 joules. That will be provided. You do not need to memorize that. Okay. Now I did a quick, this is a quick example. Let me read it because then I'll hold it up. It says, how much heat is needed to take 250 milliliters or 250 grams of water? Why can I interchange milliliter and gram? I can interchange that because the density of water is 1 gram per milliliter. So we're going to take 250 grams of water from 10 degrees Celsius to 75 degrees Celsius. That's a change in temperature of 65. It's a plug and chug. If I give you, I'm asking for how much heat, I'm giving you the mass, I provide the specific heat for water, you can do the final minus initial temperature change, you can do that. So you just multiply 250 grams times the 4.184 times the 65.0 to 3 significant figures, you get this number. Okay, now in this heat calorimetry formula, we could give you, there are 4 variables. I could give you any 3 of the 4, and you would just have to use algebra to manipulate that formula and solve for the missing 1. For instance, if I had given you this heat here and then asked you to solve for that, I'd have to give you these other 2 numbers. So it's really what I would consider a plug and chug type of formula. Now, I've got, let me see, I'm going to pull up, let's see, where is it? Here. Okay. These are the notes. Do y'all see these notes It says starts chapter 10.4. Do y'all see that? Felicia, do you see it?
Yeah, we see it.
Okay, thank you. I just went over this formula.
Sorry. Yeah, I do see it.
Okay. Anyway, this is your main calorimetry formula, where in words, it's heat equal mass times specific heat times temperature change. I just went over this. Let me admit this person. Okay. The delta T is final minus initial. I explained that the negative sign is going to mean it's exothermic, and the positive sign is going to mean that it's endothermic. I give a couple examples of reactions here. One, you guys know with the oxygen lab, you had to heat that potassium chlorate. I thought I added him in. You have to heat the potassium chlorate, so heat is needed for that reaction. And then on this one, if we were in class, I would have demonstrated a small piece of sodium in water, and I would have demonstrated that heat was released. So that's an exothermic reaction. To boil water requires heat. To freeze water, if you go, it releases heat. So the back of your refrigerator, you could probably feel that it's warm. Heat is being produced because it's trying to freeze the water to make ice. Now, here is, again, this is the endo-exothermic kind of example. This is another example. I just did one using my paper, but I'm going to go over this one because you're going to see there's a negative sign. It says how much heat is released when you take a mass of water at a hot temperature and we're cooling it to, say, a little bit below room temperature. So final 21.3 minus initial would give you a negative sign. So there should have been a negative here, but I've put it here. So when you plug in your mass times specific heat times your temperature change, you're going to put a negative sign there to show that it's exothermic. If I wanted it converted to calories, I would take my joules here and use the conversion. 1 calorie is 4.184 joules. The joules will cancel, and then you still maintain your negative sign. What I did here is to show you that if it's negative 1.58, I could change that to 15.8, and all I have to do is drop the exponent from 10 to the 4th to 10 to the 3rd. And the reason why I did this, y'all know that 10 to the 3rd means 1,000. So that's the same thing as kcals or kilocalories. Fun fact for the day, a kilocalorie is a capital CAL. And so when you read nutrition or food labels, like a chocolate chip cookie might have 250 calories, it's actually capital CAL. So it's really 250,000 little CAL calories. They do that as a space saver mainly. Okay, so that's a straight plug and chug kind of calorimetry problem. Then, okay, here I have an application. If you have, say, an element, piece of metal with a mass given, and it's at a hot temperature, and you place it in a calorimeter containing a volume of water, which is the same as 125 grams of water because of the densities being 1 gram per milliliter, and that water's at a cooler temperature, you want to find out, oh, I'm giving you the final temperature. Well, let's do the reasoning here. If you have something super hot or warm and you're putting it in something cool, your final temperature has to be in between. It can't be higher than 88.4 and it cannot be lower than 25.1. There's a reason for that, and it's this conservation of energy concept here. Heat lost by the hot pellet has to be gained, heat gained by the cool water. So basically what you're doing, and I haven't worked this out here, I want you guys to try it. It's going to be mass times specific heat times temperature change for the pellet. I'm making a substitution. Instead of the word heat, I'm going to say mass times specific heat times temperature change for the pellet equals mass times specific heat times the temperature change for the water here. And so I can back calculate the specific heat for the pellet. So I'll set it up on my board, what I'm talking about, and then y'all are going to solve that. That's going to be the first kind of thing you need to do for homework. Solve for that, and I'll send out, or y'all can just tell me on Wednesday what you get, what's your answer. Because I don't think, let me see, I don't think I provided the answer on this. Let's see if I did. No. Okay, so here we go. So heat lost by the pellet equals heat gained by the water. Now, this is the concept. That's the concept. But I am going to make a substitution. Instead of the word heat, I'm going to say mass times specific heat times temperature change. And then I'm going to write it again. Mass times specific heat times temperature change. Now, at first glance, that looks like everything's in cancel. But the stuff on the left is information due to the pellet. The stuff on the right is information of the water. So if I plug in, I know the mass for the pellet was what, 146.7. I don't know the specific heat. The temperature change, how would I get that temperature change? Somebody tell me, how would I get the temperature change for the pellet? Anybody? Or tell me what number you would get.
Is the potential minus the initial?
Oh, well, just tell me what number you would get. What minus what?
It would be the 88.4 minus the 25.
No. Nope. I get 57.1 because I took 88.4. Hold on, let me let this person in.
Oh, so you minus it by the 31.3?
Yes.
Okay.
Yes, because that's the final temperature. Now, you could, what I'm doing is heat loss equal heat gain. If you wanted to do the sum of heats to 0, you would do the 31.3 minus 88.4, you get a negative number. And a negative plus the positive is going to end up giving you a 0. But if it's so much easier just to say heat loss equal heat gain. So that's how we're going to do these. So what did I say I had got? 57.1. Okay, so that's going to be the left side. The question mark is what I'm going to solve for in a minute. The mass of the water is 125 grams. Specific heat of water I would provide, or you could look up. And what would the temperature change of the water be? Somebody. Anybody? Well, that's not right.
I got 6.2, is that right?
Whatever 31.3 minus 25.1, but I just did it. My calculator's like, I'm going to have to do the memory thing. Hold on. I'm sure you're right. I'm just seeing why my calculator's messed up. Yeah, that's not right. Okay, hold on. Let me reset it's giving me 8.
Say 6.2.
Okay, I'm going to say thank you. We'll just go with 6.2.
Yeah, that's what I got.
Okay, thank you. Okay, so now you see, I mean, I'm doing it all in one line, and I'm going to solve for my question mark. So it looks like my gram unit well, here, I'm going to hold this up if anybody needs to take a screenshot of that, because I'm going to end up
Can
erasing
you flip your screen? 'Cause
Huh?
you've got your screen in a small one where you're sharing your screen.
Oh, okay, sorry.
If you, yeah.
Okay, let me stop share. No, hold on, I'm sorry, somebody just came in the room. Okay, let me get rid of this. Okay, y'all see it now better?
Yes.
Okay, so I'm basically I cancel my units first. So I'm going to take let me get it, gram out on both sides, just canceling my unit to clean it up. Then I'm going to cancel my Celsius unit. So the only unit I have left is that specific heat unit. So if I basically multiply the right side together and then divide by the 146.7 and divide by the 57.1, I will get the answer for the specific heat of the pellet. Okay, could y'all follow what I just did? That would be considered an application of the calorimetry formula. And on the homework that I just sent, the little practice I just emailed about 8:15 this morning, I've given you a couple of the straightforward calorimetry problems to do, and then the very last one, is heat loss equal heat gain. So I'm wanting you to try that. Now I put in red all the the actual answers that I got. I mean, it's possible I made a mistake, but y'all can let me know on Wednesday. Now, your turn. Are there any questions? All I was going to do today, and for those of you that came in late, I reviewed dilution. I introduced calorimetry, which is heat equal mass times specific heat times temperature change. And we just did the application, heat loss equal heat gain. Do any of you have a question?
So for heat, that's always going to be in joules. That's the unit for that. Like the actual Q.
If the specific heat is given in joules per gram degree Celsius, the answer is yes.
Okay. And then it'd be calories if it is if it was.
Correct. And then there are some problems where it'll give you the specific heat, say like on this one, say you solve for this one and you get the specific heat is joules per gram degree Celsius. And then a part B of the problem might say, now what would it be in terms of calories? You'd have to do that conversion. Eric, do you understand what I'm saying?
Yeah, I do.
Okay. Okay, anybody else have a question? Because today was just going to be calorimetry. Wednesday is going to be Hess's Law. And I've already sent the material for that, but I'll have some lecture notes written out where I show y'all how to do it. I might actually, there's a really good video, Elizabeth Sterner, Sterner, on YouTube does chemistry videos. And she did one on Hess's Law that's really, really good. I will email that link. I'll make myself a note because I think it's really good how she did it. But that won't be, I want y'all to get your calorimetry stuff done first. Are there any other questions? Test 4, I'm pretty sure, before I say it, I'm pretty sure, I think I went ahead and put it on D2L. I've got it where I figured out your scores in front of me, but I think I posted on D2L. Could somebody tell me if you saw your, okay.
Yeah.
Yeah, so test 4 is done. Activity 5 and 6 are completed. I am going to send another activity, and it'll be a calorimetry and or Hess's law problem. I'll probably send that on Wednesday, and it'll be due, say, Sunday. In the assignments folder, this time I'm going to do it all in that folder where you don't have to go to quizzes and then go, it'll just be in the assignments folder. So let me write activity number 7. I've worked on the 11:20 one, but I haven't done the I haven't quite finished the 11:10 one, but I will. Okay, anybody else have a question or comment? Anything? Because I know we're going to get out of this, class early, but I just wanted to make sure I covered calorimetry, went over the difference between endo and exo, told you the concept, heat loss equal heat gain. Questions? Anybody? No? Don't know how I'm going to do test 5 yet. Usually it's over gas laws, and it has one Hess's law problem on it and one calorimetry problem on it. So I'm probably going to have to do it in sections, but I haven't figured out how I'm going to do that. I mean, I got the hang of looking at your work on the assignment number 6. So I had it written down in front of me how many points I'd take off if the student didn't put the states or list the electrolyte, whatever. So I was consistent, but I wrote that in the feedback. So you could see how you did on that. Anybody else have a question, or you want me to do a different problem, or you want me to make up another dilution? It doesn't matter. Just I sent you 3 or 4 dilution problems and 2 or 3, maybe 3 calorimetry problems. And that's your homework for Wednesday.
If you got a second, I'm going to do one of the dilution ones. I got stuck out in a meeting. I'd like to see one of those if possible.
Okay. Okay. I'll just do it real. Well, we'll just do this one. Okay. If I have dilution is this formula, V1M1 equal V2M2. That's your dilution formula. In this word problem, it says determine the new concentration, which means I'm solving for M2, when 10 milliliters of 0.600 molar. Okay, I'm giving you the initial volume, the initial concentration. Of in a word problem means it tells you right now that those two numbers have to go on the same side. So 10 milliliters times 0.600 molar equal, I'm adding it to 10 milliliters of water. So I don't put a 10 there, I have to put a 20 because I've got to add these two volumes. It says added to. So really it's half of that is your new diluted concentration. Now, what I went over, Nick, at the beginning, you've got to look at the wording. Added to means add the two volumes together, but look at how I worded this one. This one says, it's the same dilution formula, but I didn't say add to 50. I said added to enough water to make the total volume is 50. So this is a 50 here, not a 60. Are you seeing the difference, Nick?
Yes, I do.
Okay. Well, that's what I did at the very beginning. I did just some quick examples. And if you go back to your molarity lecture notes, at the very end of the molarity lecture notes that were emailed over a week ago, is the dilution formula and a sample, and then 2 problems where I've written the answer in red or typed the answer in red. So you can practice those too.
Okay.
Anybody else have a question? Anybody? Okay, well, Felicia, you can go ahead and stop recording. When when it converts and you upload it, could you send me the link also, please?
Yes, I can.
Okay. Okay. Thank you guys, and I'll